Dear learner, in continuation of this chapter, current electricity, today's topic is Wheatstone Bridge. First, learning outcomes. After going through this lesson, you will be able to explain the working of a Wheatstone Bridge. You will be able to apply the conditions of balanced Wheatstone Bridge for circular analysis. You will be able to apply the concept to understand the working of a meter bridge and a PO box, etc. And you will be able to synthesize your own bridge. That is, you can prepare your own bridge for the measurement of resistance. The students, we have already discussed Ohm's law, that is V equal to IR, the mathematical form, and Kichap's rule, sum of current is equal to zero at any junction of conductors. At any junction of conductor, but you know that the sum of current meeting at a point will be equal to zero. Similarly, the second law, second rule given by Kichap, so that is called voltage law or voltage rule, and the sum of potential changes in a closed loop is equal to zero. And you know how to apply the equations for different closed loops. Okay, so today's discussion, it will start with Wheatstone Bridge. It's very interesting that the bridge was not invented by Wheatstone. Right. It was invented by Samuel Hunter Christie in 1883 and was popularized by Charles Wheatstone in 1843. Basically designed for this accurate measurement of unknown resistance. And later it has been modified for different purpose for measuring of, for example, capacitance. That is Anderson bridge, and there is Wien's bridge, and other similar bridge we use for different purpose measurement of impedance, capacitance, inductance, all these things. So you can see the bridge, the design of the bridge. It is a diamond shaped. It is diamond shaped, having four diamond shaped, diamond shaped bridge. Four arms are there. The four arms. Let us call this branches. Four branches. Okay, and you can see that there is a galvanometer. A galvanometer. Galvanometer. This is the galvanometer, and we connect this the source of current. And most important thing is that this bridge is used for the accurate measurement of resistance without without any measurement of electric current or voltage, etc. Just we do what we do in Ohm's law. Here no need to measure any. We have no need to take any reading from ammeter, voltmeter, anything. What we need here we use the null deflection method. That is a null deflection method. Null deflection. That is, there will be, we have to adjust for zero deflection in the galvanometer. And when null deflection is achieved, then the bridge is said to be balanced. Bridge is said to be balanced. For a balanced bridge, we will derive the condition. Once, and from this condition, we'll be able to understand how to measure the resistance. So before that, let us distribute current. Suppose some current is drawn from the cell, and a current I1 goes through this arm having resistance P, and another current I2 that goes through this having resistance R. Here R is the variable resistance, P, Q are fixed resistance, X is the unknown resistance. This is unknown resistance. We have to find the value of X. Okay. Here I1, you see again there will be distribution of current. Let this is equal to Ig, and here the current is equal to, here the current will be equal to how much? I1 minus Ig. This is according to Kichap's law. Now in this arm, that is DC, the current will be equal to, very simple, I2 minus I2 plus Ig. Okay. Now, if we want to apply Kichap's rule, we will go through. We will discuss this based on the using Kichap's law. Using Kichap's rule, you can write. You can see for for the loop for the loop A B D A. You can see this loop A B A B D A A B D A. For this loop, what you can write, you see, if there is potential drop across P, so Pi1 minus Ig. Let resistance of the galvanometer equal to G, so Ig into G plus, let the resistance in this arm AD is equal to R, then I2 into R has to be equal to 0. Okay. If at the balance condition, once again we can we can modify this at the balanced condition of the bridge, balanced condition of the bridge. What we can write, the balanced condition of the bridge, we can write that Ig equal to 0, and therefore the equation becomes I1P plus I2R is equal to 0, or what you can write that P by R will be equal to I2 by I1, equation number 1. Now, next loop, another loop that is for the loop for the loop B C D B. What we can write? I hope you remember this. That is, this is what P, and this is U. So here it is variable resistance R, and this is much unknown resistance X. Where the galvanometer is G. Current, I hope you remember, is the power supply. Okay, current this is equal to what I1. Here it is. We have taken I2. And this current is Ig we are taking initially, but later we will make it 0 for balanced condition. That is I2 minus I1 minus Ig, and here it is equal to current is I2 plus Ig. For this loop, what you can write, you see, minus Q into I1 minus Ig plus X into I2 plus Ig plus Ig into G is equal to 0. At the balance condition or for the equilibrium condition, what happens when Ig equal to 0, for Ig equal to 0, what you can write, that is Q minus Q into I1 plus X into I2 is equal to 0, or or what you can write, X by or what we can write, let me proceed like this, Q into I1 equal to X into I2, or Q by X is equal to I2 by I1, equation number 2. Now let us compare these two equations, that is but equation 1 and equation 2. Equation 1, we can see that the left side is P by R, and right side is I2 by I1. Here it is a q by x and right side is I2 by L. So right sides equal, and therefore we can make a left side of both the equations equal, and from 1 and 2, equation 1 and 2, what we can write that p by r is equal to q by x, or x is equal to, we can write q by p into r. Now see what we have to do here in the breeze. What we have to do, see, we are taking p and q fixed. X is unknown register, nothing to do with this. What we have to do, we have to adjust r. You have to adjust R so as to achieve the current Ig equal to 0. We have to make what Ig equal to 0. Once we make Ig equal to 0, if Ig equal to 0, then we are reaching to the condition. We are reaching to the condition that P by Q, this condition can be written like this again, and P by Q is equal to R by X. So if the balance condition is achieved, then we are having in the condition that p by q equal to r by x, and from this relation we are able to find the value of x without measuring anything, without any supply of any fixed amount or specific amount of current. Right? A very small current, with very small current we can do this. We a moderate current we can do this. There is no problem. So this is what Wheatstone bridge, and can easily be used to find the resistance of a conductor. Okay, suppose resistance of a wire, we can find it. Just we have to do, in place of this x, we have to connect the unknown resistance. Now, use of Wheatstone this concept, application of Wheatstone bridge. Wheatstone bridge. One of the basic application we use in the laboratory also, that is number one is PO box, and number two is meter bridge. We use these two methods to measure the unknown resistance in laboratory in basic in class 12. But nowadays we are having only meter bridge in our syllabus. Meter bridge we have to discuss. So what a meter bridge is, let me show you what a meter bridge. Let me take a pic the from the website, and let me take this. Yes, I want to take this picture. Yes, this is what this is a meter bridge. You see, what is a bridge? This bridge is nothing but a single wire, and placed on a wooden plank. Nothing more than that. Right. Yes. You see, these are copper plates. These are copper plates, or sometimes we use steel plates, and these are screws. Screw one, two, three, 4, 5, 6, 7, 8, 9. The screws. Okay, so how to use this as a meter bridge? How we give the form of meter bridge to this a simple apparatus? And there is 1 meter long wire. Here is 1 meter long, 1 meter long resistance wire, resistance wire, and generally made up of manganese, and it has high resistivity. Now, see how we use this bridge. You see, there are two gaps, copper plate, and there is a wire between these two screws. Okay, there are two gaps. Gap one, this is G1, and here the gap is G2. Okay. In these two gaps, so one gap we will use for a fixed resistance. Let us keep one resistance box so that a fixed resistance can be taken from the box. Let this is R. R resistance will be taken from the box. And the unknown resistance will connect here. Unknown resistance will connect here. Later, this unknown resistance is equal to X. And what to do? We have to give the power supply. Here is the power supply and a bat and a key power supply. Once we let me clear things. That is yes. Yes, uh, we you can see a power is supplied here and very small voltage, that is 2 volt, 1 volt. We can use the the Glen cell also able to perform this experiment. There is no problem. So this is X, so this is Y, and we place a galvanometer. There is to this screw will connect a galvanometer. Let the galvanometer is kept here. Galvanometer, okay, okay, and a jockey, a jockey jockey, that is sliding key, sliding key wheel. You can slide over this. Now jockey, suppose it is connected at J, point J. So from point A to B, A to B, AB, the length is equal to 100 centimeters. 100 centimeters. Okay. Now how it takes the form of Wheatstone bridge, let me show. Yes, how it takes the form of Wheatstone bridge, you see. Leave the problem. Leave it. So, see, e- from let me name this C and B, A, B, that's the C and this is J. Okay, from A to C, you see there is a resistance. This resistance is R, taken from the resistance box. From C to B, there is another resistance. This is the unknown resistance X. From A to J, the simple wire is there. It also has some resistance. What is the resistance here? RAJ, resistance of the part of the wire AJ. And here is the resistance part RJB. Okay, and you see from C and J, this is A, C, B, and J. Okay, and there is power supply also. Power supply. So this, and from C to J there is a galvanometer, so it takes the form of storage. Now we are not varying the resistance here. What we are doing from the resistance box, we are not varying anything. What we are doing, what we'll do, we will slide this key. Will we will slide the key to adjust the resistance. You could understand that the what, this is the Wheatstone bridge and name. Let me give yes according to this, that is A, C, B, and J. And there is J, A, C, and B. Correct. So what we are getting, you see, if we, by by sliding sliding the jockey, the balanced condition, the null deflection is obtained. Obtained. Null deflection is obtained. And the null deflection is obtained, and it is a so it attains the balanced condition balanced condition of Wheatstone Bridge. Therefore, what we can write easily, you see, therefore, what we can write that R by X is equal to Raj by Rj. Obviously, we'll take the resistance wire uniform, okay, so that the resistance will depend only on length. Let this L and that L1, or this is equal to 100 minus L1. Sorry, this is 100 centimeter, so this will be equal to 100 minus L1. Correct. And therefore, what you can write, R by X will be equal to, is what, rho equal to linear resistivity, that is resistance per unit length into L1 by rho into 100 minus L1. Now you see what benefit we are getting here. That is R by X will be equal to L by 100 minus L1. That gives that X will be equal to 100 minus L1 by L into R. It means just finding the balancing length. That is, if we can find the balancing length here, that is at what centimeter, at what distance from the position A, at what distance from A it is balanced, there is null deflection achieved. By knowing this only, we can find the unknown resistance. We don't have to measure even the resistance. We don't have to measure the resistance. Only what we need the value of the resistance taken from the resistance box. Yeah. This is how we can measure. We can use a meter bridge to measure the. We can use a meter bridge to measure the resistance of a given wire. We can find the unknown resistance of a coil, right? So, and it is simply the form of a Wheatstone bridge. It is a Wheatstone bridge. Okay. So, dear students, and now you see, Wheatstone bridge we can use for solving problems like solving problems like say, suppose you want to find the equivalent resistance in a circuit where the form of the circuit is a Wheatstone bridge limit. Suppose there is a circuit like this. This is 4 ohm. This is 6 ohm. This is 12 ohm, and this is 18 ohm. Okay, and there is a 8 ohm resistors. You have to find the equivalent resistance between A and B. You have to find the equivalent resistance between A and B. What do you need to do? You see, just you think once that this ratio of these arms, that is 4 by 6 is equal to 2 by 3, and here it is 12 by 18 is equal to again 2 by 3. And since ratio of the resistance arms are same, therefore no current will, it is implied that no current will flow through this resistance 8 ohm. That is presence of 8 ohm and absence of 8 ohm similar. That is, we can consider in this circuit, what we can consider, that we can consider the uh, very simple, as if the resistance 8 ohm is not present here, and simply the resistance, the circuit becomes like this. That can be simplified. Simplified circuit will be like this. Now we can solve for the equivalent resistance A and B. Okay. Otherwise, we have to use Kichap's law. If they are not in balanced condition, we cannot use this concept. Okay. Now see, a Wheatstone Kichap's Wheatstone bridge is, it is very much sensitive. Some advantages is very much, number one, sensitive. It is sensitive enough. to find the accurate resistance, right? And it is it can be modified, can be modified modified forms are used to measure impedance, impedance, capacitance, capacitance, inductance, etc. Okay, one of the modified form is, for example, but Anderson bridge, and then Wien's bridge, and then but Maxwell's bridge. Like this, this can also be used to measure physical parameters like temperature, temperature, light intensity, light intensity, and strain, all those things. By using some electronic devices called op amp, operational amplifiers. If we connect this, it means this can be used as a sensor, right? Op amp amplifier we can use to find temperature, light intensity, strain, all these things, all these physical parameters. So, Wheatstone bridge is of a great help for the in the measurement of physical quantities, especially in electricity. So thank you very much. I hope you could understand how to solve problems on Wheatstone bridge. This is a very important topic for your board examinations as well as entrance examinations. And these are the basic concept. Now you can design yourself one Wheatstone bridge to measure for the accurate measurement of unknown distance. Thank you very much.